So my talk will be on the relation between possibilistic logic and abstract dialectical frameworks, and it's actually joint work with Matthias, Gabriele, Tjitze, and Kenneth. Okay, let me just, yes, okay. So the main message of the paper is actually based on, well, the observation or the fact that the semantics of abstract dialectical frameworks are based on three valued interpretations. And then the research question which we answered in this paper is which three valued logic underlies ADF. So which three valued logic is involved in the machinery of the semantics of ADFs. And it's partially inspired actually by a paper by Ringo Baumann and I think his student Heyninck, who showed in a paper which was not really on three valued logics underlying ADFs, but it's kind of as a final section, we have a very interesting result that shows that this logic underlying ADFs cannot be truth functional. And I was quite intrigued by this result, and I started thinking more about it. I thought maybe there's some hidden assumptions on the connectives, for example. But then it's a very interesting result, and we wanted then to ask which three valued logic can be set to underlie ADFs, even if it's not truth functional. Is there some logic from the rich literature on three valued logics which we know and is used in ADFs? And it turned out that this is the non-truth functional possibilistic logic known from possibility theory. So my talk is built up as follows. I'll first say, I'll introduce abstract dialectical frameworks, and I'll spend a lot of time unpacking the semantics of abstract dialectical frameworks, because I think this is, at least at the first time one sees these semantics, they are a bit strange maybe, or hard to grasp. And so I thought it would be a good idea to unpack in full detail the semantics of abstract dialectical frameworks, partially with what we know now about possibility theory in mind. And then it will turn out to be quite obvious that possibilistic logic underlies abstract dialectical frameworks. And then once I establish this connection, I'll point to some corollaries, for example, some results on the notion of models in ADFs, some results on strong equivalence, and then a generalization we made using possibility theory integrated into ADFs. So, okay, what are abstract dialectical frameworks? Abstract dialectical frameworks, as far as I can see, because I didn't invent them, they were conceived of because at some point in the history of argumentation, people started coming up with a lot of new formalisms. So as everyone knows, I think in Dumm's abstract argumentation, we have argumentative contexts which are conceived of as abstract graphs. So we have nodes in a directed graph, and the edges between these nodes represent a text. And then people argued, okay, but arguments can also support each other, for example, or we can have a text from sets of arguments instead of single arguments. And then there was kind of a proliferation of different generalizations of the abstract argumentation frameworks. And it wasn't clear how to come up with semantics if you came up with the new syntactic formalism, for example. And there was no really unified theory of this kind of generalized argumentation formalisms. And ADFs provide exactly this, this unifying model. And the idea is that, again, we have a directed graph. So we have a set of statements, which you can see as arguments if you want. And then we have a set of links. But now we don't know the exact meaning of these links. They can represent attack, they can represent support, they can represent something else. And then the idea is that the meaning is determined by these conditions. And the idea is that for every statement, we have a condition, which is a Boolean formula formulated in terms of the parents of this statement. So from the links, we can read off the language in which we can formulate this condition. And that might seem quite abstract, so I'll give you an example. For example, this ADF with three arguments A, B, and C has an attack between from B to A. So the condition here, this is read as A can be accepted if B is not accepted, and the attack is symmetric, so we can also accept B if A is not accepted. But then here, for example, we have a support from A to C and an attack from B to C. So the condition says that C can be accepted if A is accepted and B is not accepted. And this is a way to very flexibly, really determine the meaning of these links in an argumentation graph or an argumentative setting. So that's a very nice formalism. And of course, the question now is, how are the semantics of ADS determined? And the most simple semantics are the two-valued models. And there the idea is that we just have a two-valued interpretation over S. So every node is assigned either true or false. And then a two-valued interpretation is a two-valued model of an ADF if for every node we have that the node has the same truth value as its condition. So in the example we had before, for example, if we have an interpretation which assigns to A true and to B false, and then to C true as well, this is a two-valued model because, for example, the condition of A, namely not B, is true and A itself is true as well. That's how the two-valued models work. That's very straightforward. The problem is they don't always exist. For example, if we have a self-attacking argument, then it can be quite easily seen that there's no two-valued interpretation which sets A and not A to the same truth value. That's, everyone can see this very easily, I think. Okay, so then what's the solution? Well, the solution is to move from two-valued interpretations to three-valued interpretations. And the idea is that a three-valued interpretation, you can actually see it as two-valued interpretations, which are kind of an interval, which approximate the true two-valued interpretation. So we have two interpretations, V1 and V2. V1 represents a lower bound, which means that everything true according to V1 is necessarily true. And then V2 represents an upper bound, which means that everything that's true according to V2 is possibly true. So in other words, everything false according to V2 is necessarily false. And then if you kind of do the maths here a bit, one can see, I mean, this is also actually well known, that then this translates into four-valued interpretations. So for example, if the lower bound says A is false and the upper bound says A is true, then we will have that this pair of interpretations assigns undetermined to the formula A. Then if they agree, of course, a pair of interpretations will also say it's true or false. And then if the lower bound says true, but the upper bound says false, then we have an inconsistent formula. And then if we restrict these pairs of interpretations to consistent pairs, where the lower bound making something true implies that the upper bound makes something true as well, we actually have a three-valued logic. So we can see this pair as interpretations as just one interpretation mapping every atom to undetermined or undecided or true or false. And so we can actually ease the notation a bit, and we can just look at three-valued interpretations which assign every node in our ADF true, false, or undecided. And we'll denote these three-valued interpretations with this calligraphic V, and the two-valued interpretations will denote with calligraphic V with a 2. And then we can compare three-valued interpretations. There's again a nice story you can tell with these pairs of interpretations, but I'll just be looking at three-valued interpretations. So we use the information order to compare interpretations, and we start doing this just on the level of truth values. And as you would expect, undecided is less informative than both true and false, which are incomparable with respect to the truth order. So true and false are incomparable, sorry, with respect to the information order. And then we lift this pointwise. So we say that one interpretation is less or equally informative as another interpretation if every atom is assigned a truth value, which is less or equally informative than the second interpretation. So here's two very simple examples. The interpretation V, which assigns to A undecided and to B true, is less informative than V prime because V prime assigns both A and B true, and so they are comparable because for A we have undecided versus true, and for B we have true versus true. And then V and V double prime are incomparable, and that's because here B is assigned an incomparable truth value, true for V and false for V double prime. So that's the information order, and now all we have to do is just to look at how we can use this intuitive interpretation of three-valued interpretations to assign truth values to complex formulas. And so here it's helpful to bear in mind that V approximates the true two-valued interpretation. So yeah, in other words, V is somehow telling us in which interval the real two-valued interpretation should lay. Okay, so then it makes sense actually to define the set of completions, which is the set of all two-valued interpretations which are consistent with our three-valued interpretation, which we are considering. So in other words, this set of completions, it contains all the candidates of the true two-valued interpretation. So once again, it's just all the two-valued interpretations or the possible worlds which are consistent or which are more informative than the interpretation which we are considering. And then we can use this set of completions to assign a truth value to complex formulas. And how do we do this? Well, if all of the candidate true two-valued interpretations agree on the truth value of the formula phi, then we just take this truth value, and otherwise we stay undecided about the truth value of phi. And so this is then how this consensus of the completions of a three-valued interpretation is constructed. And I think from the perspective of this approximations of two-valued interpretations, this really makes sense how this is done in ADFs. And here is a small example. Suppose we have an interpretation where A is assigned undecided and B is assigned true. Well, then the first thing we have to do is to construct all of its completions, and that's quite easy. We know that B has to be true in all the completions because we already have a determinate truth value there. And then for A, we just say that A is either false or true. So these two interpretations are the two completions of this interpretation V. And then we see, for example, that the formula A or not A, so the tautology is true, because we see in all of the completions A or not A is true. And actually that will always be the case. So this logic using completions, it preserves classical tautologies and falsities. And here is an example of a formula that's undecided. For example, A and B will be undecided because there's one completion that assigns true and one completion that assigns false to A and B. So that's how we, how we assign truth values to complex formulas. And now we can just generalize the idea of the two-valued model semantics, where a formula or an atom and its condition have to be in alignment, using our way of assigning truth values based on three-valued interpretations to complex formulas. Namely, we just require that the truth value of S has to be the same as the truth value of this complex formula, the condition of S. Only now we use this way we discussed before of assigning three-valued truth values to complex formulas. And to make this a bit notationally easier, there is this gamma function which just maps interpretations to other interpretations. And the idea is that we construct the interpretation gamma PV just by assigning every atom the truth value of its condition in the original interpretation or the input interpretation V. And then, there is another example, but I won't go through. And then the idea is that this gamma function, it maps interpretations to other interpretations, and that for all of the majors, well, almost all of the major semantics of ADFs, we have that they are defined as post-fixed points or fixed points of this gamma function. So this is then, we have all the interpretations, and this is then what happens if we apply this gamma function, and then these fixed points are really the interpretations we are interested in if we look at the semantics of ADFs. In more detail, the admissible interpretations are defined as post-fixed points of the gamma function, where the complete interpretations are defined as fixed points of this gamma function. And yes, this might now seem quite technical, but we saw before that this fixed points of the gamma function, it just means that every condition of a node has the same truth value as the node itself. And then, as so often in knowledge representation, we are sometimes interested in the most informative complete extensions, the least informative complete extensions. That's the preferred and the grounded interpretation. So once again, we have these complete interpretations, and then, for example, these ones are the preferred interpretations, and these ones, this one is the grounded interpretation. Okay, that was the semantics of abstract dialectical frameworks, with a special emphasis on this three-valued logic, which is used in the gamma function, and so which is central in the semantics of ADFs. And now, for people maybe who know possibility theory, now the connection to possibility theory might have already become clear. Yeah, and so as I said already, so I will show you now that this logic defined by this consensus of the completions, it actually corresponds to possibilistic logic, one of the logics from the rich literature on three-valued logics. And so the idea behind possibilistic logic is the following. So given a three-valued interpretation, the set of completions is there actually also used, but there they call it an epistemic set. So this is just a set of completions. And then we can assign a possibility degree and a necessity degree to a formula. The possibility degree is true if there is at least one world in the epistemic set, or the set of completions, which implies phi, and it's false otherwise. The necessity degree is true if for every world in the set of in the epistemic set of V, the formula is implied, and false otherwise. And then we say that truth value given an interpretation of a formula according to possibilistic logic is true if the necessity degree of phi is true, and it's undecided if the necessity degree is false, but the possibility degree is true, and it's false otherwise. And then I think because you know this epistemic set, it's actually the same as completions. You already saw that actually possibilistic logic and ADFs, they are then use kind of the same semantics or the same logic. Yeah, just as a quick aside, so I think people are more familiar with possibility theory as with possibilistic logic. And so possibilistic logic, you actually get it out of possibility theory if you look at three-valued interpretations as a special case of possibility distribution. So normally a possibility distribution, it assigns to every possible world a degree between 0 and 1. And now if we have these three-valued interpretations, you can actually see them as a possibility distribution that assigns every world either 0 or 1. So it's kind of a special case of possibility distributions. And then, as I already told you, this epistemic set, it's actually equal to the set of completions. And if we look at now these possibility distributions, it's just a set of worlds which are assigned a possibility degree of 1. Okay, so now the results on the connection between possibilistic logic and abstract dialectical argumentation. So yes, this is already very clear by now. The possibilistic logic, it coincides with this logic based on the consensus of completions. And then we get there from there all the results on representing ADFs in possibilistic logic. For example, we can define the complete interpretations of an ADF as the interpretations where the truth value of an atom is the same as the truth value of its condition under possibilistic logic for every atom in the set of, or for every atom of the ADF. Yes, and that, so we have more results in the paper. You can characterize every semantics using possibilistic logic, and then some corollaries, which I will go through quickly because I hope we will still have some discussion. Some corollaries include some insights on models. So here the basic idea is that in the second paper on ADF, models were defined as interpretations for which if an atom is not assigned undecided, it has the same truth value as its condition, where the truth value now is determined by Kenneth logic, which now we know this is a bit surprising, but maybe back then it was not so clear what the relation between Kenneth logic and the logic that's now used in ADFs was used. And then they claim that admissible interpretations are actually tree-valued models, which is not the case because sometimes Kenneth logic disagrees with this logic based on the consensus of completions. I have an example if you want to know about it during the Q&A. And then what we did is to observe that, okay, here Kenneth logic is used, but you can define the same idea of a model using any logic. So we came up with this idea of models parameterized by a logic of an ADF. And then we defined this a logic being admissible preserving if the set of models according to this logic is a superset of the admissible models. So all admissible models are models according to this logic of the ADF. And then we studied the admissible preserving logics. And so we found out that actually possibilistic logic, which is not surprising now that we know of the connection between possibilistic logic and ADFs, that possibilistic logic, it's actually the least conservative logic, which is admissible preserving, which means that any logic which is admissible preserving will make at least as much true or false as possibilistic logic. And so in particular in the paper, we also have some examples of truth functional logics, which are admissible preserving, if you would be interested in this. Then we also have some results on strong equivalence. And here the main message is that two ADFs are strongly equivalent if their conditions are pairwise equivalent under classical logic. And that's actually, a sufficient and necessary condition. So that characterizes strong equivalence. And this is not surprising since we know that actually possibilistic logic, it uses classical logic under the hood, right? Because we have this epistemic set, but then within the epistemic set, we use classical logic. And a third corollary of our insight on the connection between ADFs and possibilistic logic is that, of course, we can now also generalize the semantics of ADFs where we use possibility distributions instead of tree-valued interpretations. So in the paper, or if you're interested in this during the Q&A, we also show how you can, given an ADF, say that a possibility distribution is admissible or complete for this ADF. So there we have kind of a numeric or quantitative semantics for ADFs, which is a generalization of the normal semantics of ADFs based on tree-valued interpretation. Okay, so this brings me to the conclusion. So I hope to have convinced you that possibilistic logic is actually a logic that is central for the semantics of ADFs, and as was already demonstrated by Ringo Baumann, that no truth functional logic can mirror this behavior. And corollaries include insights on strong equivalence and possibilistic ADFs. So yeah, thank you for your attention, and I'm happy to take any questions or comments.